Hello and welcome to this week's episode of Google Maps Developers Live. I'm Paul Saxman, and with me this week is Brendan, the Tessellator Kenny.
That is what they call me.
Yes. And this week we're going to talk about some advanced visualization techniques using OpenGL or WebGL.
Mm-hmm.
And specifically, you're going to talk about a library that you recently ported from C to JavaScript, right?
Right.
To do exactly what your title describes.
Right.
Tessellation.
Yeah. So this library, it's I don't know what I'm trying to say. It's a little bit of step back. It's not necessarily an application. It's more of a tool that you can use for applications. And so we're going to mostly talk about the tool itself today and show like some examples, but not anything that'll be like really mind blowing. It'll be more like this will be useful if you need this sort of thing.
I don't know. So, I mean, maybe for the uneducated of us, maybe explain like what tessellation actually is, because it's kind of for graphics guys, it's pretty straightforward. But
so the reason that we need this, so in the past we've talked about how it can be useful to draw WebGL stuff on top of a map. It gets you a couple of things. It gets you really good performance for a lot of things. So say you want to put even millions of markers down or something like that. You can't do that today with Canvas or any of the mapping libraries out there. So you need to cluster or generate tiles or whatever. But with WebGL, putting WebGL on top of a map, you could do that if you wanted to. You'd have to think about usability of those millions of markers, but you could if you wanted to, is the key.
And we talked about the trick with all this is using what we presented at a previous show is the canvas layer.
Yeah, so there's the canvas layer library. You can just Google for that, one word, it's the top result. And it's in the Maps API utility library. And what it does is it just sticks HTML5 canvas as a layer in your Google Map, and then you get a handle to it, and you can draw whatever you want to it, whether that's 2D canvas or WebGL. So points are easy, but a lot of geographic data is in the form of polygons, and the problem is that WebGL can only draw triangles. That's the simplest primitive there is that has area, but the fact is that most geographic data actually stores things as polygons, both for efficiency and because that's kind of a more natural way to describe like an area. Mm-hmm. And so you need something to be able to draw polygons. So you get speed, but you can also do things like you can start getting custom effects per pixel and like do crazy lighting or adjust things based on like demographic data or whatever. All these things are unlocked when you can really do fancy WebGL, especially if you want to do it for say every county or every country or political district within some area. So the key is that we need to make triangles out of polygons. And then there's another layer of things where geographic data is also extremely messy usually, whether it's coming in real time, in which case you have an excuse for polygons to backtrack on themselves and intersect with themselves and have repeated vertices within their descriptions. Or when you don't really have an excuse, you get a file from a customer or something like that, and it's maybe the file format says that all polygons have to wind a certain direction and not self-intersect, but inevitably someone will give you a file that's horribly garbled, and you need to display it on screen. So you have to deal with both of those things. We have to make triangles, but we have to make triangles out of nasty data.
And there's also donuts, right?
Right, yes. And so then you can have multiple, like in KML, rings where some define inside and some define holes on the inside of the polygon. So it's complicated. And so we kind of looked around a few months ago, and we're looking for kind of libraries that would let you do that and do it efficiently. And there wasn't really a lot of options. There's a few triangulation or tessellation libraries out there, but they're not necessarily super fast or super stable and really let you throw anything at them. So I decided to port the glue tessellator, which is the GLU is the OpenGL utility library from years gone by. It was originally, late 80s, early 90s is most of the code. So generally about 20 years old.
A kind of interesting piece of trivia is it was probably written over in the Google main campus, which was then SGI. So
right. So the implementation I was looking at was the SGI open source implementation, which was written like just a few blocks next door. And so it actually says you can go to that address and get your software license in writing, even though SGI's Google's there now, not SGI. So let's take a look. If you go on GitHub and you look for libtest.js, so libtest is the name of the library. It implements the glue tessellator interface. You can see it, and right now you see license information, and actually there's no examples right now, so I'm going to rectify that after this with the example that we're about to look at. And you can see kind of how it's used. It's a little esoteric. It's very C-like, so it was originally C code. And I left it as close to the original interface as possible when I was porting to make sure that it worked. And now that it's working, I'm going to start looking at options for a more JavaScript interface. There's lots of enumerated property values that you pass in and flags. And there's a weird mix. And I don't know if this has to do with just historical reasons, but there's a weird mix of, for some things, you actually pass in callbacks. You pass in function pointers in the C code. And sometimes it's like you get this insanely long switch function based on different enumerated values. And so it's a weird mix. And there's no reason it needs to be like that, because there's not going to be a lot of legacy code that people are going to be using here. So why not make a new interface? But for now, it's very C-like, which is what we're going to be talking about today. So so you can see the information and the license. The license is kind of a weird SGI-specific license, but the Free Software Foundation has actually worked with the remnant of SGI to get it under a nice, friendly license, and now it's fully compatible with all your. It's BSD-like, but it's also compatible with all your other copyleft licenses. So feel free to use it, rip stuff out of it, do anything you want with it. So let's take a look at an example first. Sound good? All right. Let's go full screen. So here is all the, it's basically zip codes, but it's actually pseudo zip codes from the Census Department, Bureau, whatever, in California. And I think we have, I don't know, a few 100,000 triangles make up this drawing. This is actually from a shapefile parser that Manomarks ported over to JavaScript. And so it parses a shapefile and then takes all those polygons and runs it through the triangulation, the tessellator library, to make polygons, and then fills them in with random colors. I just picked random colors, but you could imagine that this is based on zip code data or demographic data. And I think we actually showed this a month or two ago on one of our visualization sessions with Mano. And if we get down to it, you can actually see this handles well even cases where there's holes within polygons, where there's smaller zip codes within larger zip codes. And if I open up the console here, ooh, that's fun. But let's pop it into here. If we open up the console, we can then make a function. Let's see, change places, I call it. And so what this does is it loops over all the counties or all the zip codes and assigns a random color to them. It just picks a random RGB value and assigns a random color. And then I call schedule update on the canvas layer, which just calls a paint. And so if I call that, everything will change to a random color. And then if we just want to make sure that we have the proper kind of disco party feel, we could actually put, let's put that in an interval, because why not? It's like the blink tag, but for maps.
Don't cause any seizures.
Yeah, so I'm going to put it 500 milliseconds, so it's a little slower. We could do it at the frame rate if we wanted to. And now,
that's the amazing thing, right? I mean, so you have I don't know how many polygons on there.
I think this comes down. Yeah, I don't know. Actually, I should count the number of counties, but you can see like even or zip codes. But even in LA, you have just a crazy number of, including these ones. I don't know if that's due to the post office or if it has something to do with gerrymandering at some point in the past. I guess
like political boundary.
Yeah, like follows rivers, and I guess that's because they tried to get it neighborhoods maybe at some time in the past. But yes. You can make really amazing, beautiful maps like this, but the key is that we're redrawing all these triangles in real time, and if we wanted to do it 60 frames a second, I could do that, but I'm refraining because I don't think the video will even record.
Brendan, you've reinvented the blink tag.
Exactly, for maps. So if we refresh here, I can show you a little bit. I can switch the mode so it's actually drawing lines instead of polygons. So this. It doesn't draw all the triangle lines because I'd actually change the triangles to do them differently. But if we zoom in on one of these zip codes, we can see kind of what's going on. So it's not the prettiest triangulation. It actually it breaks things down into these monopolygons, which are polygons that are easily splittable with triangles. So you have some more modern techniques involve like Delaunay triangulations where you can get like optimal angles where you maximize like the size of each triangle. But the nice thing about this is that it's super stable. It's also well tested. It's 18-year-old code and libraries and software projects will just import it directly and not make any changes because they know that it's been so well time tested that everything's stable.
And it works.
And it works.
I mean, you have like you can get 60 frames per second out of this code.
Right.
I mean, or your tessellation, it looked like it took about about a minute.
This took
1 second.
Less than a second. Yeah, 800 milliseconds for about I think 890 triangles. 890,000 triangles is what you end up with. And it can be faster. When you profile it right now, about 20% of the time is spent on garbage collection, which we can eliminate. We have the technology, but that'll come in the future. So it's fast, and yeah, Delaunay triangulation is not necessarily bounded except for if you make compromises. It's execution time. And for graphics, this is usually fine. You can deal with these skinny triangles and do per pixel effects. If you're doing like a numerical simulation where you're showing like the spread of heat or I don't know zombie infections or something, you might run into some numerical problems with these skinny triangles, but it's fine for the most part. And you can tell it's completely stable even as we zoom in. Way in here, these things share border, and as a result, you can't see any break between them, stray pixels. So that's this. It's pretty exciting. It's pretty fast. So
what are some applications of this? So you mentioned we can actually get all the counties in California.
Right.
So what are some other things you can do with
this
I mean, technique?
As I said, it really comes down to like we have geographic data that's in polygons, and we need if we want to draw polygons, we need some way to draw polygons. So anything you need to draw a polygon for today, you can with this. So that's not necessarily an application in itself, but any reason that you need to. So an example would be if you have effects per zip code, but if you imagine zip codes for the entire United States, and you want to change that per frame, there's nothing right now that you could draw that in real time. You could draw it statically. You could draw it to 2D canvas and not change anything. But as soon as you pan or zoom in, you'd have to redraw it all again, and that takes some time. And this would do it virtually instantly. But then as soon as you want to like run effects across those, like you wouldn't be able to do that at 60 frames a second.
Can you do things like, for example, instead of filling the polygons, can we actually just get the stroke and stroke the polygon?
Yeah, so you can get that outer border. And the cool thing about that is that you can actually adjust the winding order and then do kind of shape algebra. So you can you can find the union or the intersection of different polygons, and you can do that in real time. And so if you wanted to do something like take the area of some effect, like some environmental thing, and then intersect it with zip code data to find out exactly which zip codes are affected by this. You could do that, and you could do that, offline or something already, but this lets you do it at 60 frames a second, and as you like move your blobby thing around, you can find out that intersection. It also, the great thing about libtest is that it will take extremely degenerate polygons. It'll take the nastiest polygons you can throw at it. It'll take any winding order that you want, so whether you want it to be clockwise is inside and counterclockwise vertices is outside, or the opposite, or you have two clockwise but you want to count one as the outside, you can just specify that you want even winding orders to be outside if you want. So it's
really friendly to kind of dirty geographic data,
right?
Which we regularly see.
Exactly, which is actually most geographic data. And you don't necessarily have time to sit there and say, well, they input this data, but they probably meant this data. So do you mean fix it this way? Instead, it's like, just draw something, and if it doesn't look reasonable, then you say, okay, let's fix your data. You don't want to sit there and say, well, I can draw it for you as soon as you have reasonable data. So here's the example that I'm going to be including with libtest in the repository. And this is just a simple triangulation. And all I'm doing is kind of making a circle and then just adding a random radius to each point as I go around the circle, just to give you an idea. So we can look at the actual code that does this. And as I said, it's kind of nasty C code, C-like code, which is it's very flat, and there's no real object hierarchy you have to worry about. But on the other hand, it's very verbose, and you have to think about all the different properties you have to set. So here's the triangulate function. If we look here in DevTools, and you can ignore this. It's the triangulation actually supports triangulation in 3D, so you can actually do an X, Y, Z, but we just set 0 for all our Z coordinates. And so I have this, I call it Tessie, but it's the tessellation object you just call new glue tessellator. And when you're ready to start, you say begin polygon, and you pass it the array that you want to put your final vertices into. You loop over contours, it's called. Sometimes they're called rings. Sometimes they're called faces even. And that's each ring of vertices that make up your polygon. So a polygon can be made up of multiple vertices, multiple rings or contours. And they could be both additive, so that they actually add area to your polygon, and they could be subtractive, so they actually take away and make holes in the polygon. And so we just loop over our contours. And so for each, we have begin polygon on the outside. Inside of that, we have begin contour and end contour. And you have as many of those as you have contours. And then within that, you have vertices. You set each vertex one at a time. So here for each contour, I begin contour. And for each contour, I then loop over vertices. And for each vertex, I then add that vertex. And then finally, we say end polygon, and that's when it actually does its calculation and spits out your triangles. So here I'm just getting the triangles directly, but there's a lot of things you could do with things like just give me the outside border, or give me, it can actually split it up into triangle fans and triangle strips if that's more efficient for your use case. And there's a couple of different things it can do. And then you can do crazy things like get the outside border and then run it through it again and triangulate the outside border, so that you're not ignoring all the internal lines that you might have had to generate triangles, whereas by default it will actually generate triangles within those.
And all these functions are built into libtest, right?
Yeah, it's all built in, yeah.
So we have some kind of documentation on kind of these public methods.
So it's all documented. It's closure style docs, so it's even typed if you want that. You don't have to use it. It's not enforced. It's just enforced by the closure compiler. But the nice thing about that is that it can compile down and eliminate dead code. And I think it's about 7K with gzip. So it's pretty small when you get down to it. So finally, I get an array, or sorry, this array that I passed to the tessellator in the beginning is now full of my triangles. And now I do my normal WebGL stuff, which you can look up elsewhere. But you could use 3JS, you could use any library you want, or you could use plain WebGL, which is what I use in this example, to create an array buffer, pass it to your GPU, and then say draw it. So, so you can see here in this example that I'm drawing this polygon, and every time I refresh, it adds different randomness. And so this takes about 9 milliseconds to tessellate. But that's actually misleading because that's before the V8 has had time to profile itself and then run crankshaft to optimize your code. So this gets down to less than a millisecond usually when you run it through a couple of times. So and now I can do the same thing and set filled mode equal to false and schedule an update. Oops. And you can see once again the lines that are drawing here, which is exciting. So what I do here is I just generate a circle, but let's say I wanted to add another circle to make a donut, as you said. So I can go back to my code and uncomment this. So this just makes another contour. So I have an array of contours. This makes another contour with a slightly smaller radius. And I set a counterclockwise flag here. So the internal one, the slightly smaller loop, will be clockwise, so it's opposite. So now if I go back to Chrome and I refresh, I now have a nice thing here. Very exciting.
Can we see what the polygon or the triangles look like?
So it's a little confusing because it's drawing these lines which aren't actually there. They're actually, because they're individual triangles, if the next triangle is like way across the polygon, it'll actually draw a connecting line. But it's enough to give you an idea of what it's doing. Is it'll actually create the two borders and then find those polygons that it can easily triangulate first. Not quite greedy, but not that far off to find what it can tessellate. And so yeah, so there you go.
And as a developer, you're not that worried about the lines. I mean, once it's tessellated, you're not working in triangles. You're still just working in polygons.
Right.
And you can get the vertices out.
It's more WebGL needs to worry about that, but it interpolates it across correctly. And as you can see, there's no visible artifacts. And as we refresh, we can see the nice dance of. And so this scales fairly well. If we go back here and we can say.
Cool question. Are all the vertices part of your original polygon? So the tessellation library doesn't create vertices. Is that true?
Let's see, is that correct? Yes, except intersections. So where lines intersect, it will split both lines and insert a new vertex between those. Now the 2 line segments become 4 line segments. So yes, other than that, it won't create any new vertices, which is part of the problem with some of those uglier tessellations is that really what you want to do is like create internal vertices and use those to kind of split up the space. But that becomes a much different problem because then you're minimizing energies rather than just doing a kind of more deterministic kind of working through your vertices. So just to show that this is very possible, we can scale this up to like 5,000 vertices because why not? And suddenly we get kind of this insane fuzzy thing here.
Which is just because you're scaling the radius.
Yeah, so the radius is a random kind of 0.1 plus or minus, and so you get kind of this really fuzzy. Whoa, I don't know what happened there. And it's actually somewhat difficult for the tessellator because when they're so close, they might be intersecting, and so it has to check every time you get a new one. It actually has to check from on either side if it's intersecting, and as it's a sweep line method. And so anyway, the point though is that it can handle this quite rapidly without any issue. So and if we do this again, we can see that the lines become almost as complicated as the filled version. So to the point where it's no longer useful, unuseful visualization. So that's it. I'm going to put up this example up, and so that should make the library a little bit clearer. and then look for some interesting applications of this in the near future. But I just wanted to get this out there and get people introduced to it. And I look forward to, if you have any issues, if you have any suggestions about the JavaScript interface, if you have things that you wish that it could do but it can't, let me know. I'm going to be working on performance and the JavaScript interface, and yeah, that's what's coming up.
All right. Well, thanks a lot.
Yeah.
So thank you, everybody, for joining us today. Again, if you want to find the code, GitHub, search for libtest.js.
So there's a lot of libtests, but there'll be, and libtest too,
Yeah.
but there'll be C, so you want to look for .js.
And examples coming. And if you guys have any questions, comments, put them in the comment section of YouTube, and we'll get back to you as quickly as we can.
All
So thanks again,
Yeah.
and see you next week.